Hi there, this is Paul Edwards with Danmar Company. Today I'm going to be discussing the new Danmar One Button Dispenser, and I guess One Button Dispenser is kind of curious commentary for this new design and dispenser that we're handling now. The purpose of this dispenser is really to act as a metering system to a downstream flow, and I'm going to get into some detail about that in just a second, but right now I just want to talk about safety first. Anytime you deal or work with a chemistry that involves maybe corrosive materials or maybe very close to corrosive materials, we always recommend that you use safety glasses, nitrile gloves. As you see, those are upside down. So my preparatory work is questionable at best, but yeah, those shouldn't be upside down there. So I got my safety glasses, my nitrile gloves, and we also included today a nuisance odor mask. And what I want to describe nuisance odors is that right now the OSHA regulates hazardous odors above certain parts per million in air, and so if you're above OSHA's limits, then that isn't considered a nuisance odor. But if you're below it, and I would suggest significantly lower than the allowable exposure level from OSHA, then you want to wear a nuisance odor mask, and those are available through Danmar Company. They have a carbon filter that is part of the matrix of the mask itself, and it filters out a great deal of odors. So that's pretty good design there. Anyway, back to the dispenser. The dispenser is considered one button because it has one button. Okay, so when you press that button, okay, the neat thing about this particular button is, if you could tell, you can put it in a mode where it's only on when you press the button. That's kind of cool. I like that feature. You know, it's only on when I need it on. Okay, so I'm going to try to get this a little bit focused on here so that we can go on and take a look at that really well. Okay, so making my little adjustments there. So I'm going to press that button. You see this? Bam, 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 bam. Okay, now you push it and twist it to the side. Guess what? It stays open. That's what we're going to be working with right now, is it's staying open. What I mean, open flow. Okay, so the water is entering at this end and it's coming out at this end, and as it goes through this Venturi, chemistry is sucked in right here. So this is a siphoning design on the one button dispenser. So I'm going to be talking about siphoning designs versus positive displacement, or water-driven positive displacement, and water-driven like this one here, water-driven that is not positive displacement. It's a siphon design, siphon technology. You might be wondering, okay, Paul, why are you not wearing gloves? Well, first of all, anytime you work with a training environment, I have always recommended that you use water to demonstrate with. So that's what we're doing, is we're using my safety principle, which is to train with water. Okay, so that's what we're doing. We're training with water. Now, if we look closer at this unit here, and I'm going to go on and bring your attention here to the side of the unit. Okay, notice here that there is this little chamber there, and then underneath that there's a T fitting. Those are items that can be purchased through Danmar. Okay, let me explain what's going on there. Okay, so below is two tubings, and those two tubings are going directly into a 50-gallon pail. Excuse me again, 5-gallon pail of water. Okay, so there's water right in there, and So because I'm working with water, I feel comfortable with the fact that I don't need to work with nitrile gloves, okay? And that's the only time that I would, you know, it's okay. I mean, I could wear gloves right now, but my hands would get sweaty inside because I'm outside and it's going to get hot today. And I don't want my hands to get sweaty, so I'm just, this is water is cold. I want my hand to get in cold water. These are all brand new tubing, so it doesn't have any residual chemistry in it. So I'm just playing with water right now. Notice that this thing here has a ceramic weight and a filter check valve. Okay, that is the purpose for the filter check valve, is so that you can go on and filter debris, as well as you can go on and it has a check valve in it that does not allow the water that's in that tubing to exit the tubing, okay? So that's the purpose of check valves, to make sure that that happens, okay? Then you have a ceramic weight. I'm going to put the ceramic weight in there. Now sometimes those check valves and those filters, they're better designed by other companies, and sometimes they're not, you know, and I happen to like this one here, although I also have a blue one that I show a lot, and that blue one's made by another manufacturer. And so either way, you can get the this check valve or the other check valve. When you place an order on check valves, there's any number of places it could be brought in from, okay? And then the last thing I want to demonstrate is what I used to calibrate this unit, get an understanding of calibration. You see the end of that right there? It's got multiple orifice sizes. That's very important. We're going to be talking about that multiple orifice sizes and how it affects the performance of this unit. So basically what's happening here, if I could give you a general overview of what we're looking at, is we're looking at a dispenser that's designed to go on and stay on. So basically water is fed into the inlet side there, and because I have that that button depressed, it's going to stay on. So the pressure in that hose, the water pressure in that hose, is still water pressure through this line here at the exit point, right here, discharge point. So that means that this line is full of water and pressure. Now what I'm going to do is I'm going to take this valve, this spray head that I just showed you, and I'm going to open it up, and I want you to listen to the sound here. Okay, what I'm doing is I'm spraying a plastic can with the water pressure coming out of the hose. Okay, you hear that? Okay, now I'm going to turn it off. Okay, that flow that you just heard is a flow that can be measured, okay? And I'm gonna go over all those methods here in just a second, okay? But more importantly, what I'm going to do is I'm going to talk to you about what type of flow rate is minimally required for this unit to work in the scenario that I've created. The scenario I created was 50 feet of hose, and the 50 feet of hose is being operated through this unit. Okay, so you have an inlet hose of about 150, excuse me, you have an inlet hose of 50 feet. You have an outlet hose of 50 feet, and those two hoses right there is a combined flow distance of 100 feet, okay? So you have 50 feet on the inlet side, 50 feet on the outlet side. The combined distance through that dispenser is 100 feet. And so basically what's happening here is that we just witnessed that at the flow that we're operating at, we basically had that kind of an outcome. Okay, so you might be asking yourself, well, what kind of outcome exactly did we have? Well, first of all, we're going to back up a little bit. We're going to take a look at this tubing. This tubing right now is filled with water. So what I'm going to do is I'm going to take this glasses, I'm going to toss it over there. I'm going to toss my little anti-odor device there, filtering device. And I'm going to go in and focus on the tubing for right now, okay? So I got the tubing sitting right there, okay? Now the purpose for my pulling the tubing out of the water is I want to show you what happens when I open up this volume again. And in this particular device, it's called full volume. I'm going to open up that full volume of water, and remember that volume is not only based by pressure, but it's affected by distance. So the fact that we have 50 feet inlet, 50 feet outlet, that's affecting it. The dynamics of a siphoning device, and so pressure is going to affect this. The distance of the hose is going to affect it, and the last thing that's going to affect it is the volume of water. So if this pressure was established on air and water, then yeah, that's going to be different. But if you have a fully volumized hose, which we have right now, volumized with water, and we open up the floodgates, per se, then you see what's happening there. Do you see the bubbles that are starting to accumulate? And if you look really close here to the T-fitting connection, look very close, folks. I'm sorry, it's hard to look close. See how it's just sucking air now? This just completely sucked all the solution just with this flow rate out of that tubing. Now I'm going to put the tubing back in. Okay? Now did you see that it filled up again? You saw it filled up again. Now I'm going to take the tubing out. And watch, it's gonna, you see the air passing through it now? Just sucked all the contents out of the tubing. Okay. Okay, now I'm gonna put it back in again. Okay, now all of a sudden it's drawing the solution back in through both tubings. I'm gonna lower this again, so I want you to see what happened with this tubing right here, okay? Okay, you look at that. Now what I'm going to do is I'm going to pull the tubing out of the wire. Okay, you see it sucking all the solution out of the tubing, and maybe a little bit of... Okay, see that? Okay, one of the things that you might do is you might make sure that what you have here is you have a fully operational design that is drawing evenly. Sometimes the flow rate allows for even drawing, sometimes it doesn't. But that could or couldn't be an issue depending on whether you have a measurable difference. Okay, so that's the question: is do we have a measurable difference? Now what I'm going to do is I'm going to change. Okay, now I've changed the shower. I'm sorry, not flower, shower. Okay, what I'm going to do is I'm going to pull this out again, the tubing. Okay, once again, it's sucking both lines free with shower. So basically what's happening, folks, what you're witnessing right now is the dynamic of flow or siphoning based on your volume. Okay, and I can tell you that you can measure that, folks. Okay, you see this dynamic that we're looking at? The fact that both these tubings are drawing chemistry at the same time at different degrees. One may be higher than the other. That's just the inherent challenges that we see with these divided chemistry flows like we are. And I'm going to put it back in. See, now it looks like it fills both. Okay, but when I put it back in, both tubings fill up. So as long as, what I'm trying to say, as long as you have a flooded suction on that tubing that it's completely filled, you have predictable outcomes. But whenever one container runs out of chemistry and the other one runs out of chemistry, the suction of an empty container is going to be different with this design. Now that's not bad. But what would happen with the positive displacement pump? Well, positive displacement pump would continue to pump, whether it's there's chemistry in the container or not. It's going to continue to pump, 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 pump. So when it's pumping, it's going to pump either liquid or air, okay, but equally, okay, because it's pumping. It's designed to push. So it sucks and push, sucks and push. What we're seeing here is more like suck, 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 and no pushing, because it's sucking into a water stream, And that's different when you're sucking into a water stream versus having a pressurized motor pushing the chemistry through. So that's a fundamental difference there of these two designs. But for the money, okay, it's worth looking at this type of a design versus a positive displacement. Positive displacement system replacement. Let's say that you have you bought a packaged like let's say a OLSTI or a Dosmatic or any other positive displacement pumps. There's all kinds of motorized, electric motorized. I'm not going to go into all the different Aldus, Grundus. There's plenty out there. So depending on where you're at with the design, but it's the expense is different. So you're looking at a Grundus pump, or you're looking at OLSTI. You're looking at pumps that cost you, $5 grand, $4 grand, $3 grand. Just a replacement pump of an OLSTI is anywhere from $2,700 to $3,000. So they're not inexpensive pumps to replace. This one right here, if you're replacing it, that we're looking at, where's my finger? This one here, I'm pointing up here. We're looking at about anywhere from $75 to $100 replacement, and that's if you're replacing the whole thing. If you're replacing just the injector itself, that injector's right there is about a $40 injector piece. So I mean, it's very reasonable to look at this design and say, hey, you know what, that's something I want to consider. So the big fundamental difference, of course, of the positive displacement versus this unit here is, which is a siphoning design, is cost related, and the other difference is one is motorized force that's driven by water, where siphoning is more like a siphoning. Okay, positive displacement, pressure behind the push. So when you got flow moving through there, you have pressure pushing your flow. There's some sort of a motorized pressure, whether it's a water hydrodynamic pressure or whether it is a electric motor pushing. That is different from siphoning, something that's sucking a vortex that is being created based on the volumetric suction that's occurring from the design of the injector. So I hope I explained that, folks. There's people smarter than I am that could go into the science of those, and these manufacturers have a great deal of talented scientists that you could talk to about that. And I try to get all that information the best as I can and provide it to you so that you can go on and become a scientist yourself and develop that. So anyway, let's go back to these parts that we're back to, and then I'm going to try to wrap this up here. So basically, you've got this chamber here. I call it an activation chamber. What happens is the surface area that the chemistry, and in this case we're dealing with two raw chemistries. If you're using our biosecurity Danmar design biosecurity, you're actually looking at two of these dispensers and a set of these siphoning assemblies, and one of them is sucking in an alkaline detergent called PE5 ND, and then the other one is sucking in the a sanitizer, which it could be Proxene, which is what we carry, or it could be a calcium hypochlorite that we carry, and it could be also sodium hypochlorite that we can get you. Could be other types of sanitizers out there. So I just want to tell you that it's not limited to its capabilities and regarding the chemistries that you're talking about. Then I'm going to go down here to that T-fitting. The T-fitting has these little tips. I gotta grab this so you can take a look at it. Okay, these T-fittings have the tips. So that means that you can go on. You see that little thing right there? You guys see that little tip? That thing's small. Okay, got a little small little hole there. It screws in to this tip assembly right here, this T assembly. It screws in right there. Screws in right there. And it also can screw in at the very top here right here. So you have 3 places that you can screw these little tips in, and these metering orifices, they're designed to give you accurate chemistry flow. Okay, so I will work with you, Paul Edwards, Denmark Company. I will work with you in getting the correct titrations based on your test kit. We always do everything based on your test kit, give you your accurate chemistry fitting. So have a test kit. If we're going to talk about problems that you might be having, that we're always going to talk test kit results. Okay. And so basically, now the last thing I want to do is, this is closing comments, is basically what I want to do is I want to demonstrate that we just looked at 2 flow rates in full and in shower. That basically what I did was I filled up the tank, and this 5-gallon pail, I took this this head at the setting that I had it at. Where's that head at? I'm trying to get it on my camera here. Where's that head? There's the head. Okay, what I basically did was I started filling up this tank, this 5-gallon pail, with that head positioned, and I measured how long it took to fill up that 5-gallon tank. And in 2 cases, one was 1 minute and 45 seconds. The other one was 2 minutes, okay, to fill up the 5-gallon container. And that's with the water pressure that I have at my location. Water pressure changes some places, and so that flow rate changes. And that flow rate, you need to know what that is at the front end. Because if you ever call me up with a technical question, I'm going to ask you, what is your flow rate? The way you measure your flow rate is you stick your outlet head, you're going to stick it in a container, and you're going to come up with a stopwatch, and you're going to measure how long it takes. So right now, I could tell you that based on those 2 configurations, see this video, it'll actually show you the math. But I just want to let you know that that's very important, because if I was to take the same mist head, okay, and I put this same head, and I go on and put it at mist, okay, which I'm going to do right now. I'm going to turn it on. You hear that? You don't hear it banging against that plastic can, do you? Okay, you don't hear it, right? Well, look what happens with my little tubing here. Okay, no bubbles. Okay, now that's not to say that no chemistry is being sucked up. I'm not trying to make that statement. What I'm saying, though, it's not visibly working. It's from a visible standpoint, it doesn't seem to be working. But let me ask you this: if we were to prime this, okay, with the chemistry, and we ran it like this for about 30 minutes, because you remember we got 50 feet of hose that we're trying to fill up the chemistry with this misting head. It's going to take a while before we see the effects make its way 50 feet, okay? So you got to be patient here, okay? I'm teaching you about patience. So about 30 minutes, 40 minutes down the road, you know, depending on what your flow rate is, you're going to have whatever solution's being siphoned verifiable, meaning that you can see the bubbles, okay? You don't see the bubbles right now, okay? But I'm going to go and turn this head back to full. Now look at this. Hear that? See the bubbles? Work with easy to use flow rates, okay? If you want to run a misting volume through your system, go with the positive displacement pumps. Don't mess with these siphoning designs. Don't mess with them, because they're going to be hard to work with and manage them and validate. But then use this kind of design. It's inexpensive, it works, and you'll see with later on with other videos that I do that in a biosecurity environment, you want to work with flow rates that are going to give you the maximum reduction of bacteria by two ways. First of all, the volume sufficient enough to break up the biofilm with your PE5ND, and that once you've cleaned up the biofilm, that you can use your sanitizer to both rinse off the surface and also rinse a clean surface. So I would do a double rinse with a sanitizer rather than a water flush. I would do a double rinse with sanitizer. We're talking about biosecurity here, folks. Biosecurity, as I see it, as my definition, is that you are resolving a potential problem that has a history of being a problem. So if you're calling some area biosecurity area, that means that you know that the probability of a organism to develop there because of the bacterial load already present, then that's a biosecurity, a biohazard environment, in my opinion. And so basically you have to have a flow rate that's going to meet that demand to address that area. Now the metering tips are going to assure to you that you have the right mix of your sanitizer and the right mix of your detergent. I won't be discussing that on this video, but just telling you that that's what you want to work with. Your preliminary equipment design has to be able to work with you in a viable way to use your alkaline detergent and your sanitizer. Well, that's enough from my standpoint. I thank you very much for your business. If you have any questions, you can email me directly at danmarco1@msn.com. That's danmarco1@msn.com. That's a number 1. You can visit me at my website, www.danmarco.net. That's www.danmarco.net. Or you can call me directly at 817-822-5767. 817-822-5767. And remember, safety first. Thank you very much.